Hi everyone, this is Education with Eleanor, and today we're doing Newton's law of universal gravitation. Our question is asking, what is the force of gravity in the following situation? Earth's moon on an 80 kilogram astronaut standing on its equator, and part B, an 80 kilogram astronaut standing on the moon's equator. So we've got this astronaut here, and then this is the equator, and the astronaut is standing here. Okay, and there's the moon. So this is to give you an understanding of what does this all look like. And this will be the distance between the two objects. Now, I'm going to talk about this a bit more, but I need you to understand that, and that will be R. The first thing is, which of the gravity equations do we actually want to use? Well, first of all, you've often seen F equals mg. This is actually a bit more specific, something we need to get a bit more specific about. This is planet specific, and it calculates the force of gravity on a specific planet, or what we also know as the weight. So that's why I've got F with the subscript g here for the force of gravity, and it's equal to the mass of an object multiplied by the acceleration due to gravity based on that planet. So, if you were on Earth compared to if you were on Jupiter, the acceleration due to gravity is much more than the acceleration due to gravity on Earth. So you will have a different weight even if you have the same mass. Now, the equation we're actually going to use today is Newton's law of universal gravitation, and this will work always. Now, I'm also going to link another video below done by another channel called Flipping Physics, and they go into more detail about Newton's law of universal gravitation, or understanding gravity even more. Now, this equation, it's the force of gravity, and it's equal to the gravitational constant multiplied by the first mass multiplied by the second mass, then divided by the distance between the two centers of masses squared. So that's something we need to understand. This R over here, we need to understand it's the distance between the two centers of mass between two objects. Sometimes it is the radius of a given object, but not always. Alright, so let's understand this. Let's go back to our diagram. We have the moon here, and the center of mass of the moon is over here. The center of mass of the person, of the astronaut, would be roughly there in the middle of the person. But if you think about it, the radius of the moon is so large compared to the height of the astronaut that adding that little tiny bit of the astronaut would be rather inconsequential. So we're going to ignore the height of the astronaut in terms of figuring out the center of mass of the astronaut. We're just going to assume it is actually the radius of the moon, or the equatorial radius of the moon. So let's get the data that we need. For those of you who are in my class, in your textbook there is an appendix that has astronomical data, and this is where we got it from. This data that I'm about to go through. So, the first mass 1, is the moon. And the moon, we're saying mass 1 is the moon, and the mass of the moon is 7.35 times 10 to the positive 22 kilograms. And then the mass of the astronaut, which is in the question, is 80 kilograms. The gravitational constant is 6.67 times 10 to the negative 11 Newton meters squared per kilometers squared. Whoops, let's get rid of that red decimal point. I was trying to make that just a bit better. Now, the radius. In this case, the radius is the equatorial radius that we're going to use in that particular table. Okay? Alright, so let's do part A. So with part A, we're going to look at, we've got the force on the astronaut by the Earth is equal to 6.67 times 10 to the negative 11, and that'll be, if you have your units, newtons meters squared per kilograms squared. Now the first mass 1, is our moon, so that's multiplied by 7.35 times 10 to the positive 22 kilograms. Then you multiply by the mass of the astronaut, which is 80 kilograms. We divide that by the distance between the two objects, the two centers of masses, which is 1.74 times 10 to the positive 6, and that's meters, and then all of that will be squared because r is squared. Now, note that I have put your brackets or the brackets around that r value, the distance between the two centers of masses, in red. Now, I'm also going to do that for our other scientific notation figures. The reason being is, if you don't enter it in like this with your parentheses around those numbers in such a way in your scientific calculator, it is highly likely you'll get the wrong result. Alright, let's keep going. You enter that into your calculator and the answer will start to look like this, 1.295. There's more decimal places, but I'm not writing them down. It's times 10 to the positive 2 newtons. Now, let's have a look at our original data. Let's figure out our significant figures. So the mass of the moon, 1, 2, 3 significant figures. The astronaut, it is 1, 2 significant figures. And then the gravitational constant is 1, 2, 3, and your radius, not radius, your distance between the two centers of masses is 1, 2, 3, 3. So the 80 kilograms is 2 significant figures. Now, for those of you who are watching outside of Victoria, Australia, in VCE, all zeros in a number are considered significant. It's the rules of our curriculum, and that's why there's 2 significant figures there. So we need to round down to the least amount of significant figures, so that will be 1.3 times 10 to the positive 2 newtons. Okay, and because it's the force of the astronaut on the Earth, the force will be towards the center of the Earth. Let's look at part B. Part B, we're asked to find out the force on the Earth by the astronaut. That's going to be equal and opposite to the force on the astronaut by the Earth. So that will equal negative 1.3 times 10 to the positive 2 newtons. And then if we wanted to get rid of the negative because we want to put a direction, it'll be 1.3 times 10 to the positive 2 newtons, and it'll be towards the center of the astronaut. Okay, so this is, I'll zoom out a bit, an example on the law of Newton's law of universal gravitation. And I hope you liked this. If you did, press the like button and remember to subscribe and hit the notification bell for more videos. Bye!